Hello everyone. In the last lecture, we have discussed how to draw the stick diagrams, what are the various rules that can be applied to draw the stick diagrams. And I welcome you to now the stick diagrams of various logic gates as a various examples. I'm Jyothirmai Joshi, Assistant Professor in the EI Department, VNR, VJEC. So if we want to discuss the various logic gates, we already discussed one of the logic gate, which is NOT gate, nothing but the inverter. Now we'll be going on with NOR gate. So this is the schematic of the NOR gate. We know the expression, what is it? Y is equal to A plus B whole bar. Generally, we have various logic gates like OR gate, AND gate, NAND gate, NOR gate, XOR gate, etc. All the gates can be represented using these layouts and the stick diagrams, because the basic IC design flow uses these MOS transistors for their design. Hence, every circuit has to be reduced to the transistor level, that is a MOS logic level. Here, this is the representation how we are seeing. And we also understood that whenever we are trying to draw the schematic diagrams, always the output of this MOS logic will be the complementary part. Therefore, it's easy for us to understand first what is NOR gate and then go with the OR gate. That means now this logic directly gives me the output, which is A plus B whole bar. How do we draw this NOR gate? If you try to see A plus B. This is a representation of two transistors in parallel. So this is input A, this is input A, this is input B. These two are transistors which are in the pull down side, which will represent a logic. So understand one thing here, the pull down always gives the logic. Pull down always gives us the logic. Pull up is complementary of it always when we are trying to draw other gates like NOR or OR gates. So here, this is the logic. It is A plus B. So these two are parallelly connected here, two transistors parallelly connected at the pull down side, and at the pull up side it's exactly the complementary of it. That means here we are drawing it parallel, means in the pull up side both will be in series. So that's what is the logic here. See, A plus B is drawn here as a two parallel combination. Above the demarcation line, we have the pull-up side where both A and B are connected in series. The same thing we have to represent now as a layout and the schematic. And I already told you, when we are trying to draw the layout, it is a block of those metal, poly, N diffusion or P diffusion drawn as blocks, and stick diagrams are represented using sticks. So this is what is our layout that we get, or we can say simply the sticks will be the stick diagram for this corresponding NOR gate. If you try to understand, see here, we have taken two sticks of N diffusion, right? This is one stick, this is one stick. We have drawn them parallelly and we have put a contact here, right, in order to make a metal contact, metal and diffusion contact, and we cross them with the poly. This is how we need to cross with the poly. And see, we have given, this is a parallel combination of these two. And here on the pull-up side, what are we doing? This pull-up side, we are taking a P diffusion. This is our P diffusion, where we are putting a transistor representation with poly. And we are connecting them through poly here. So this is how do we draw a stick diagram or layout for a NOR gate. If I want to draw OR gate, what should I do then? Simply you can understand. See, what is this here? It is A plus B whole bar. If I try to complement it, what happens? Double complement will be giving me A plus B. Therefore, just simply if I draw a inverter here to the output of this one, I can easily implement a OR gate here. Got my point? And similarly to this output, we will give a inverter circuit, inverter schematic or inverter stick diagram. And how do we draw the generally how do we represent the inverter? The inverter circuit will be, here we'll be having the PMOS, here we'll be having the NMOS, and when we try to attach them and connect this to VDD and connect this to VSS here, this is our inverter circuit, and here we take V out. This is general schematic for OR gate. So just adding an inverter will convert this schematic diagram to OR gate. And similarly here we'll draw the stick diagram, extending these here and drawing another N poly here, P poly here. This is what you will attach these two and apply the input here. We will attach these two and take the output. So this will give you the OR gate. And next, if you try to understand another example here, what can we do? See, this is just N notation A into B plus C whole bar. If you just see the expression itself, it is in complementary notation. If it's in complementary notation, it is easy for us to represent using our logic gates because there is no inverter required here. And A into B first is a series combination of A and B, right? A and B will be connected in series and C will be connected parallel, right? So this is how we need to connect at the pull down side. I already told you pull down side will be the logic. Therefore, A and B, here the A and B are connected in series, and for that we are connecting C in parallel. Therefore, this gives us a logic of A into B plus C whole bar. And complementary, exactly complementary at the pull-up side. So what are we doing here? We are taking A and B in parallel and in series with C, exactly complementary of pull-down side. This is how is the schematic. How do we draw for this example of A into B plus C whole bar? And when we try to draw the stick diagram for this, this is our VDD, that is power. This is our VSS ground. What did we do here? We are trying to represent A and B in the pull-up side. Because those two are in a parallel combination, right? And here, pull-down side, what will we do? We will connect AB here as a series. So this is how we are trying to do. See, the B is connected there. C is in series at the pull-up side and parallel at the pull-down side. So this is how we need to draw it. I hope you understand how did we draw this, how the series and parallel combinations are made here based on the schematic diagram, right? This is our N diffusion if you understand, and this is our P diffusion, and this is how we draw the schematic diagram as well as stick diagram for our this example, right? Then if you can take, now we can take an example of say NAND gate. If you want to take the example of NAND gate, the expression that we know is it is A into B whole bar. The schematic will be simple, right? What will be the schematic for this? This will take a demarcation line. When we are drawing the schematic, it will be easy for to understand. So pull down side, what will we do? We will draw two NMOS transistors representing a series combination. Here, and this is ground. And when it comes to the, this is VSS. And when it comes to the pull-up side, what are we doing? We take two NMOS transistors. Please try to understand. If you are not putting this dot here, it won't be PMOS. So this is PMOS device A and B. It's exactly complementary, which is at the pull down side. So this is the pull up side. where we are exactly drawing the complementary of, and this becomes our VDD. And here what do? We take V out here, and we can make the connections of this in this manner. This is a metal, so it won't be interfacing with the poly lines or other lines. So this is what we can attach. If not, you can just representing using all those A's and B's. That will be sufficient even. You need not even specially draw a line connecting those. It itself tells that we are giving a representation of A and B inputs, so that is sufficient. You need not draw this line because it will be confusing. And correspondingly, you can take the stick diagram, right? Drawing the VDD and still lines here. And what will you do? You take a P diffusion, N diffusion here, and you take a P diffusion here. As this is not a parallel combination required, what will we do? We'll just draw this line, that is sufficient. We'll put a via here, we'll put a via here, we'll put a via here. And you will draw A and B lines here, A and B. See, please understand that I'm just trying to do with a pen. So this will be green. This will be poly, which is red, obviously. And we will try to connect. This is A and B again, inputs, and we'll try to connect this using a metal. And you can make a contact here, and you will take V out here. And you already gave the inputs. If you want, you can make a connections for A and B with a poly. So this is how can we draw a stick diagram, right? And if I want to make this as AND gate, the simple logic that I can do is simply double complement it. That means I'm just adding an inverter here. If I add an inverter here, this out here will be V out bar, right? Here it is VDD. Here it is VSS. Therefore, what happens? Now the V out bar is nothing but A into B, which is nothing but the logic for the AND gate. So this is another example where we can see for understanding the concepts of logic gates. Similarly, if it is XOR gate, what can we do? This is just a simple representation, right? See, these are the layers. This is monochrome encoding that we can do. See here, these are the layers: blue with a metal, red with polysilicon. This is another way of representing our stick diagrams, not only with the sticks, right? This is a contact via. And the connection rules. See, please remember that generally whenever we cross N diffusion or P diffusion with a poly, it is a transistor. If you put a via here, that cannot be a transistor. It is no more a transistor. You need to understand that. Okay, these are the rules which are representing those. Just now we have understood the connection rules for it. This is another example. Just now I discussed you. This is nothing but a NAND gate. This is a two A and B inputs in series, and exactly pull-up side is a complementary of it, which is a parallel combination of A and B. And this is the pull-up logic which is represented here, right? You are taking a green and crossing it with a poly, and this is a metal contact, right? This is the easy part which will tell us a logic. And pull-up side, how can you draw? There are many forms that we can draw the pull-up side. See, this is how we understood first initially. We have taken P diffusion and crossed it with a poly. We have taken P diffusion and crossed with the poly. This is our VDD line, right? And the other form is, see, you can also draw in this manner. You can take P diffusion horizontally and cross it with poly. You can combine these two and also make the connection of pull-up network. Here again, this is another format where you can see this connection is parallel, which is made here. Using any of these pull-ups, you can draw your stick diagram. This is what is a complete stick diagram representation using how can you draw. This logic is used here. Okay, this is another way that you can draw it. Then Just now we saw using monochrome coding, how can we draw this NAND gate and inverter? So this is blue VDD, right? Then this is our P diffusion, this is our N diffusion, crossed with the poly and made a connections with the vias. This is the NAND gate structure with a series of A and B and in the parallel combination of A and B at the pull-up side. Right. If you want to see XNOR examples, how do we draw the XOR gate? XOR gate logic is nothing but A into B bar plus A bar into B. So for this logic, general representation is we can directly take A and B bar to each of the transistors, make the series combination of it as well the parallel combination of it. But this is another representation that we can do for this. See here, you are using two inverters. This part, please try to observe. This part is, we are getting an inverter output A and B bars, A bar and B bar. So implementing this structure, implementing this schematic will give you your output of XOR. What are we doing? We are taking a series combination of AB and series combination of ABR, which is put in parallel, and here at the pull-up side we are taking A and B bar, the logic, and A bar and B. This will give us a logic of A bar plus A bar into B, and the corresponding stick diagram is drawn here with all the connections made for this structure. Completely this structure it is implemented here. And you can also do simple way. This is somewhat making us complex, but instead of that, what can we do is, for the XOR gate, simply you can take it as, you know, the logic is A into B bar plus A bar B. Therefore, you can simply draw it as, take a demarcation line. Your logic is nothing but two transistors A and B bar, and this is nothing but A bar B. You can connect these two, right? This is our VSS, and simply go upside. What do we get? This combination will be now parallel, and to this again this will be in series. So you can take it as the upside has, here there is another logic with the combination of, if suppose this is A B bar, this will be A bar B. These are PMOS transistors connected in exactly complementary form of pull up. This is pull down. This is exactly complementary form of your pull down ratio. So this can also you can draw with a schematic, and this can be very simple way of implementation of your XOR gate. Right. If you take a two input multiplexer, generally what do we do? This is how is the multiplexer logic that we take. Right. We take a select line S0 and we take AB. If S0 is 0, you take the output is A, and if S0 is 1, you take output as B. You can as simply implement this logic with a simple circuit, taking S0 as, here you can draw it as A will be the input, right? And you will take this as A into S0 bar, and this you will take B into S0. That's what. Simple these combinations. You will write A into S0 bar plus B into S0. This will be your Y0. And simply put A in series with S0 bar. And simply in parallel with these two, B into S0, and exactly complementary at the pull up side. And this will be your VSS, and here this will be your pull up, exactly complementary of it. This is how we can simply implement it. The another way that we can represent this is, see, here You have taken A and B. If S naught is 0, B will be as an input, and if S is 1, A will be the input, and that will be passed to the output. This is another way of implementation using two NAND gates, and this is your OR logic, right? With a complementary inputs. This is how you need to implement. Just directly drawing the schematic of this also will work out for a two input multiplexer. This is how is the few examples. If you want, you can implement any of the examples for drawing this logic. You can take anything. You can put any logic here. You can say A plus B into C whole bar. If there is no bar here, no complement, the simple form that what should we do? We have to add an inverter to it. Suppose say we'll take here an example of A plus B into C. If this is the case, what will we do is, we will take a demarcation line first. The pull down side is a logic. Therefore, what can we do? We will take, sorry, we will take A and B in parallel, right? Because A plus B, and this will be our VSS. And here you will draw the series combination with C. This is our pull down side, and pull up side is exactly reverse of it or complementary of it. What will we do? We will take AB as a series combination. AB are taken as a series combination and in parallel with C. This is your VDD and this is your logic for this one. Now, what is our main aim? It's not just directly bar. It is complement. I mean, it is A plus B into C. Therefore, what should we do? This input has to be connected to the inverter. So, simply what will we do? We will put a inverter here, which will give us the logic of this, which is nothing but A is equal to A plus B into C. And the corresponding stick diagram is similar to it. And this is how we'll end up the session here with a few examples that we have discussed. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.